I really should lower that volume.
I think it's kind of epic, you know?
It does make sure you know the lecture's starting. So we are going to continue with heat engines. We will finish heat engines today. I know I've been going a little slow on this thermodynamics. It seems like I haven't done enough. Like last night, I talked to Ryan. Ryan gave me a suggestion of making some worksheets for you. So I was thinking about, worksheets, problems, what kind of problems do I put on there? Kept me awake last night. Not things that you have to, Ryan said it might not be popular with the other students. It wouldn't be worksheets you have to turn in. It'd be things you could practice with that I would then also have solutions on YouTube for you to listen to and watch. So that's another thing to add to my Thanksgiving list. But anyway, so I was thinking about problems, and I was like, wow, I don't think we've even done any calorimetry problems. That's a problem. So I'll put calorimetry problems on those little, worksheets just so you have that experience. So you can look forward to that. Let's get on with this. Talking about heat engines. A heat engine, what's the purpose of a heat engine? It's really important that we know that, or else we're just spinning our wheels, so to speak. To make mechanical energy from? Thermal energy. And of course, remember, the first law of thermodynamics says you can't create or destroy energy. It's a conversion process, converting it from one type to another. And the second law of thermodynamics, one of the statements is that heat naturally flows from a hotter object to a colder object. But another statement is that it's impossible to make a heat engine that converts all of the thermal energy into mechanical energy. You're always going to have some waste energy. So that's why we have a temperature hot here. That's the temperature where heat is coming from a high temperature source, which it naturally will flow out of. We have a temperature cold down here, the temperature of the exhausted heat that leaves. And then we have the work that's coming out. So heat is going out of the hot into the cold with work coming out. This is what we like. This here we want to optimize. So when we talk about the efficiency of the engine is the thing that we wanted out, the work, divided by what we put in, the QH. And so, in a happy, perfect, non-physics world, we would be able to convert all of that heat that went in into work out. We'd have 100% efficiency. But in a real world, we're always going to have some exhausted heat. In fact, we learned that for a complete cycle, the change in internal energy of a heat engine has to be zero. Right, Trace? What happens if it's not zero, Trace? He had an unfortunate event yesterday. I'm not rubbing it in. I'm using a practical example right here. Oh, my. Maybe.
I'll get hit once.
Yeah,
don't buy 20-year-old vehicles. Just don't.
Uh-oh.
20, yeah.
Okay. I asked my astronomy class last night how old I was, and one student answered 74. Just,
Oh.
I think Eli suggested that student's going to fail the class. Okay, so we have change in internal energy is zero for a cycle, and since delta U is equal to the heat added, which would be to my engine, Q hot flows in and Q cold flows out. So there's the heat added minus the work done by the system. If that's zero, that gives me a relationship that says the work is equal to Q hot minus Q cold. That's really simple. That's just conservation of energy. So I can rewrite the efficiency as Q hot minus Q cold over Q hot, or 1 minus Q cold over Q hot. In that final form, it makes it real clear. If you could make Q cold zero, you would have a perfect efficiency. But you can't do that according to the laws of thermodynamics. James? So we are going to examine this more carefully. Here is an automobile engine. Oddly enough, no relation between the words. An automobile engine uses what's called the Otto Cycle. That Otto there is the last name of a German scientist. But it's kind of easy to remember because an automobile uses the Otto Cycle. We call it a 4-stroke cycle. You have first intake. You have your fuel-air mixture that's pulled into the piston. What's happening to the volume during that intake? It's expanding. So if we look at this diagram, I'm actually going to go down here. Which of these there are 4 sides. Which of the 4 lines is the one with volume expanding? C to D. So I'm just going to mark on here intake. Now it shows it here as an adiabatic process. What would it mean for it to be an adiabatic process? It's what? There's no heat. That's right. That's a process wherein there's no heat. What would make this an adiabatic process? What would make it have no heat? There are 2 options that you can come up with, and it's kind of a combination of the 2. Temperature is related to heat, but not equal to heat. What'd you say?
Really fast.
Okay, it goes really fast. Remember the video we watched yesterday of the aircraft making the cloud because the gas was expanding really quickly, so there wasn't time for heat to flow in, hence the temperature was dropping. So if it's really fast, that would be one option. What would the other option be for no heat? You have people who are bundled up in clothing, more than the minimum. Why? Okay, to prevent heat loss. If it's well insulated, you would also have no heat. So you have those 2 options. So the car engine, it's reasonably quick. And while metal's a pretty good conductor of heat, the gas inside is not a very good conductor of heat. So it's considered adiabatic for that expansion. Then the next step, compression. Pistons going back up. What's happening to the volume then? Okay, so the volume is getting smaller. So that's going to be this one here. Notice going from D to A, that wasn't listed. Now what we're going to see is there's something on this cycle that's not listed. Then we have the power stroke. What's happening during the power stroke to volume? It's expanding again. This 4-stroke is going to go through 2 expansions and 2 contractions. Our diagram only had 1. You have these. You have intake and exhaust, intake is going from here to here. So there's my intake. And then we have this expansion that's compression. That's the compression stroke there. And then what comes next? There are 2 things that happen real quick. You have the spark. What's going to happen when you have the spark? Okay, you ignite the gas, you have the temperature suddenly shoots up, right? And so on this diagram, if the temperature shoots up and you have in an instance the volume's not changing in that instant when the temperature shoots up, so it's a constant volume and the temperature shoots up, so the pressure goes up. So this here is combustion. So you compress the gas, then you combust it. It suddenly is a hot gas. There's no time essentially for that combustion step. Then the next step is the expansion. That was called power here. And then we have the exhaust. During the exhaust, heat is going out. So that's the exhaust cycle. And then, so the heat is released. That's like an instant. And then it doesn't even give a name for the piston moving this way when it finishes the exhaust. So that's actually the diagram. It had two lines that weren't shown. This is idealized. Even with my perfectly horizontal lines, it's idealized. But what they showed was just the fundamental parts we use for analysis. I had another picture that was a more realistic picture, and I decided to just stick with the basic one. But that's what's going on for the heat engine in our automobiles. The heat comes from burning gasoline. Now, some interesting things about that burning gasoline that we think about occasionally, but not enough. What is octane measuring?
This may be wrong, but I thought it was the heat generated when burning.
It's actually not. That's what I thought too until I started studying this. It's not. What does the term octane mean? All you organic chemists here.
It's an 8-carbon chain.
It's an 8-carbon chain. Originally, that's what octane measurement was measuring, how many chains you had that were, I think it was under 8 carbons. It's now a little more complicated in the measurement, but it started with that, hence the name. But the octane is telling you about how quickly the gas burns. Longer chains take longer to burn. Shorter chains burn more quickly. If you have gas that burns too quickly, then you put a real hammer on the piston. And so you can have what we call pinging in a car. A car is pinging when the gas is burning too rapidly and hitting the piston so hard that it makes the piston actually rock, which, as you can imagine, is not good for your cylinders or pistons. So a higher octane will make it so it burns a little slower. So it doesn't hammer it right now, but it pushes over time more. So that's what's really the difference in the octane. It's not the energy content. Now, what is going to change the energy content of your gasoline? The ethanol. The ethanol is going to change your energy content. We get less energy when we put ethanol gas in than when we put straight gas in our cars. So there is some energy in it. It's cheaper. Are you actually getting more miles per dollar? I saw a talk at the physics conference we go to second semester where these guys started exploring it, but they were undergraduate students, didn't have time to do all of their research and didn't have the answer. But that was their goal, to determine if it would be better to buy the cheap ethanol gasoline or the more expensive straight gasoline. So this is the Otto cycle. What efficiency do we get out of automobile engines? What percentage of the energy contained in the gasoline do we actually get that we can use to drive our cars? Does anybody know?
30.
Okay, Nathan says 30, I think. Toyota has announced that they have an engine that they claim gives you 38% efficiency. That's a small engine, by the way, 1 or 1.3 liters. It's a pretty small engine. But they claim that they can get 38% efficiency out of this. If you have a diesel engine, the diesel engines get slightly better efficiencies, around 40% or more or so. So diesel engines are more efficient than gasoline engines. They tend to also be more polluting. So 38%, is that good then? It depends.
Compared to other vehicles, yeah, absolutely.
Yeah, compared to others. So when scientists are trying to develop a more efficient engine, they want to know how much room do we have to improve. Can they improve all the way to 100% efficiency? Kind of rhetorical, but can they? No. Second law of thermodynamics says they can't. And so, in fact, we have an engine that we can calculate what the best possible efficiency you could get is. And that engine is called the Carnot engine. Notice my words, ideal and impossible. I've seen people say, oh yes, somebody made a Carnot engine. No, they did not. The Carnot engine is based on transitions that we've seen. You have an isothermal expansion. What does isothermal mean? The temperature is constant. So you have a constant temperature expansion followed by an adiabatic expansion. What does adiabatic mean? No heat. Then you reverse it and you have an isothermal contraction and an adiabatic contraction. In this process, you have it has a change in entropy for the entire cycle of 0. In order to make this work, you would have to have an infinite amount of time to go through one cycle. So if you tried to do everything super perfectly, and if you had an infinite amount of time, you might be able to get through one cycle of the Carnot engine. But why it's useful is because you have the heat flows in, obviously not on an adiabatic process, but on the isothermal process. And for the isothermal process, heat is proportional to temperature So if you have a higher temperature, it's going to have a higher heat, lower temperature, lower heat for the cycle. And so if we do the efficiency, the efficiency for this engine is 1 minus temperature cold over temperature hot. I just substituted because of the proportionality. And if we did it carefully, you'd see that, yes, it does work out for the cycle of 2 isotherms and 2 adiabats. The temperature cold over, or Q cold over Q hot is temperature cold over temperature hot. So we can calculate what the ideal efficiency should be, and then we can take a real engine and say, how close is it to the ideal efficiency? We know no matter how we create an engine, it's not going to exceed this efficiency. If we get close to it, we'll feel good. So I looked up numbers. This is what I was doing for the last half hour before class, trying to find accurate numbers for the temperatures of an automobile engine. I found some sources with wildly different numbers, but I think these are reasonably close. The high temperature for an automobile engine, that is the temperature of the burning gas, is around 2000 Celsius. And the cold temperature, the temperature of exhaust coming out of the pistons, is around 400 degrees Celsius. So you have a pretty good drop in temperature as the gas expands. So what's the efficiency ideal? We put efficiency Carnot for the ideal efficiency. What numbers do I need to put in here? Put what?
400 over 2000.
It needs to be in kelvins. That was why I asked the question. So I need to convert the 400 to 673 over 2273 kelvins. And so what is the Carnot efficiency for the automobile engine? I know I saw something that gave a number. So we'll see if my numbers match theirs. Yeah, it's exactly what they suggested the ideal efficiency would be. Feeling better. What does that give you for an ideal efficiency? Okay, 7039. So I'm going to put 0.704. So 70.4% would be the best possible efficiency you could get burning gasoline with the typical exhaust temperature. If you lower the exhaust temperature, what's that going to do to your potential efficiency? If temperature cold goes down, what's your efficiency going to do?
Increase.
It's going to increase. So the cooler we can make that exhaust temperature, the more efficient we can make our engine run. And so engines today have, at least from what I was reading this morning, cooler exhaust temperatures than they used to have, because as they've developed more efficient engines, you're getting less of that heat coming out, lower temperature. So now we take this number and we compare it to Toyota's claim. They're a little bit over halfway to ideal. Is there room for improvement? Absolutely. Is that improvement going to make a difference in my pocketbook? Absolutely. How do people work on improving engines? Well, a big part of it is motorsports. Those guys in the motorsports are advancing the technology about engines. They're not working on fuel efficiency all that much. They are a little bit, because if you can get better fuel economy and still the same power, then you have less pit stops. You get to the end of the race, when people are running out of gas, you might be able to keep going. So they do worry about that a little, but they worry about getting the most power they can per ounce of gasoline, which is going to translate into higher efficiency again. So those guys who are working on making super powerful engines are actually doing a real benefit for the rest of us in developing better technology so we can have more efficient engines in our car. Okay, so we've done one calculation there just on the efficiency. There's lots of calculations we do that are simply of the order of, if we have Q hot is equal to 700 joules and efficiency is equal to, let's say 0.38 for that Toyota engine. What is Q cold? How do you do a calculation like that?
Well, if you understand that the efficiency is a ratio,
Mm-hmm.
you could use it as to solve for the other one, if you know one.
So efficiency is what we get out, the work, divided by what we put in, Q hot. Or since this didn't have work in it, that's the equation I would use if I was looking for work. But I want the Q cold, so I'm just going to replace the work with Q hot minus Q cold over Q hot equals 1 minus Q cold over Q hot. And now I have an easy calculation. 1 minus Q cold over Q hot is equal to 0.38. Rearrange that. 1 minus 0.38 is equal to Q cold over Q hot. So 1 minus 0.038 is 0.62. And there you have it. So it wasn't super hard. So that's the kind of problems that we are typically going to have with the heat engines. Either the calculation relating workout, Q hot and Q cold with efficiency, or the calculation of Carnot efficiency. Now, on this idea of heat engines, pretty much everything we have comes down to running as a heat engine. And there's a lot of interesting heat engines we have. Now, if we talk about heat engines, one of the very common heat engines is what we use to produce electrical power. Electrical power, we boil water. We have a boiler. What's boiling the water? Traditionally, we burn something. We burn oil, or we burn coal, or we can burn some other things. We can burn biomass. That is, we're taking trees and shrubs and brush and burning that biomass. Something has to generate the heat to boil the water. And then that hot water is going to be used to drive steam turbines. Steam turbines are more efficient than pistons. That is, you can adjust the pitch of the turbine so that you just keep pushing and pushing and pushing until you've used up virtually all of the higher pressure, the pressure difference, and you exhaust a much cooler gas, steam. And so you're pushing on these. The pushing is doing work. It's making it move. And then that motion, as we'll learn next semester, is turning a generator to produce electricity. So you get electricity from your work, right? The work is making the turbines rotate, and then that rotation is being converted into electricity at a very high efficiency for that conversion, because that's not converting thermal energy, it's converting electrical energy. But then we're left with this steam. So what do you do with that steam? You have these cooling towers. You've all seen cooling towers, I'm guessing. Those cooling towers have one simple purpose. You put some cold water around the exterior, the steam comes up, the cold water around the exterior will cool the steam, cause it to condense, and drop the water back out. So that you're not blowing hot steam into the air, you're just cooler air coming out. So when you have these power plants, you often have a cooling tower. Obviously, water is a major component for a power plant. You need the water. Well, one thing is you need the water for your boiler. That water you're going to want to keep. You're going to want to keep it clean. And if you look in the system, the water that they're using in the boiler is not the water that goes to the cooling tower. They use a heat exchanger. And so the water going to the cooling tower is not the stuff in the boiler. Stuff in the boiler needs to be really clean. The stuff that's going to the cooling tower doesn't have to be. So you can, for instance, build this on the side of a water body, and you just bring in stream water or ocean water, whatever, and use that ocean water as the cooling water that goes into the cooling tower. And you have your isolated water in the steam system that is ultra clean. So when you look at power plants, you almost always find them on bodies of water so they can use that water as part of their cooling system. Now I said you've got to have something to boil the water. I didn't realize this when I was your age. A nuclear power plant is also a steam power plant. You're using a boiler, turning a turbine. What's the difference in the nuclear power plant versus the coal? It's what you're using to make stuff hot. The nuclear power plant is converting mass into thermal energy, because mass, according to Einstein, is just a form of energy. You might have learned at some point that mass cannot be created or destroyed, but that is incorrect. Mass can be created or destroyed. It's just a form of energy. The first law of thermodynamics is the immutable law. You cannot create or destroy energy. So nuclear power plants often have cooling towers that look just like those in a normal coal or oil-burning power plant. I put here a picture of San Onofre. San Onofre doesn't have cooling towers. Why do you suppose it doesn't have cooling towers? It does need to be cooled.
Because they live next to you?
Yeah, they are just running their pipes out into the ocean and cooling using the ocean. And so they don't have a not fractioning tower in this case. They don't have cooling towers because they're using ocean water itself to cool their hot water. Going off of the physics topic and into society, nuclear power, good or bad? How many people say it's good? Okay, that looks like a majority. How many people say it's bad? Andrew said from the outset, I don't know, so he voted both ways. Now, since Andrew said, I don't know, I'm not going to pick on him and say, so why'd you say bad? So I will give the bad arguments for you. Reasons why nuclear power is bad. First, we have to put the caveat, when we say nuclear power, we mean nuclear fission power. Nuclear fusion power, everybody agrees is good. What's the problem with nuclear fusion power, Nate?
It's not really useful.
Well, we don't have a way to control it. The sun controls nuclear fusion just fine because gravity controls it. But when we make nuclear fusion, gravity here on Earth isn't enough and it just makes a bomb, kablooey. So controlling nuclear fusion is the problem with nuclear fusion for power plants right now. So nuclear fission is all we have for power plants. Nuclear fission means that you dig rocks out of the ground that have an unstable nucleus. The nucleus is kind of like this is, say this is balanced. If I have this balanced, it won't be balanced for long. It's going to fall over. That's what happens in the nucleus. The nucleus is unstable. It's going to fall to a lower energy state and in the process release energy. So when you have that occur, that energy is released. In a nuclear power plant, we're using that energy then to heat water. Sounds fair. But the problem is, when this unstable nucleus relaxes, it will do something like break up into two different nuclei. That's what we're using in a nuclear fission power plant. The fission is breaking into two smaller ones. And those two smaller ones themselves are not stable. And so those are going to break up further. And what you do is you end up making products that are still radioactive. They're not giving off enough energy to be useful for boiling the water, but they're giving off enough energy to be not safe for us to be around. And so what do you do with that? You have this wasted material that you can't do anything with. So that's the big problem with nuclear power. What are you going to do with your waste product?
Yes, I did the same.
That has been proposed. Some things that could go wrong is every now and then we have a failed rocket launch. And if you had a failed rocket launch with a load of radioactive material, we probably wouldn't be happy. And so I think that's why that one never materialized. But smart minds came up with the same idea you guys did. It's not a foolish idea. It was a good idea, just one that didn't pan out. Another idea that the U.S. government, in our wisdom, spent millions of dollars on, and then in our wisdom, decided that's enough, and stopped after spending millions, is to dig out a mountain in Nevada. Nobody lives in Nevada. Dig out a mountain in Nevada that is filled with salt. And then you put the radioactive material in the salt, and you pack salt around it, and you leave it. And you consider it safe because that salt is not going to allow water to flow through, so you're not going to have water flow through and take radioactive material down, out of it. It was an idea that was really popular. Like I said, Congress funded it, and then they defunded it. Congress has a way of doing things. You guys all know about CERN and looking for things like the God particle. There was a superconducting supercollider built in Texas. You guys are probably too young. You do know about it. Most people your age are too young to know about it. Used to have a colleague here, Scott Anderson, who actually worked there when they were building it. Unfortunately, they were almost done and Congress cut the funding. I think it was billions of dollars spent on building the world's greatest particle accelerator. And then the funding was cut and they decommissioned and spent a whole lot more money decommissioning the thing.
To be fair, I only know about it because of the Flash.
Oh, the TV show or the comic book character. All right. Well, that's fair. That's the way you learn about things. So there's the negative for nuclear power. Another negative some people will say is, well, you're going to have pollution into the atmosphere. I don't want to be close to a nuclear power plant. It's going to be putting radioactive materials into the atmosphere. That is a completely false concern.
Yeah.
That's a false concern. Nuclear power plants are very well contained, except for in the random case like, Chernobyl.
Wow.
Chernobyl, they got a little carried away. They were trying to see, from what I've read, they're trying to see how hot they can make the reactor and then how quickly they can cool it down. Got it too hot.
Not a good idea.
Yeah. Failed a little. But I don't think we've ever had that kind of problem with the U.S. reactor. They don't emit radioactive waste. It's just the stuff that you're having to haul away. In fact, the coal power plants have more radioactive emissions than a nuclear power plant. You're going to get higher radiation levels because there's radioactive materials in everything. Each one of you is radioactive. Not very much. The coal has radioactive material in it. When you burn the coal, you release the radioactive material into the atmosphere. Yeah.
I read something a while back that if you had like a nuclear power plant in your backyard, or you were sitting next to someone, like you'd get more radiation from that person.
Yeah.
Is that true?
Yes, I believe it is.
Okay.
Because we shield those power plants really carefully to make sure they're safe, whereas you don't shield your friends. Right? Your banana, your milk, plenty of radioactive.
I think that's very true. Like, as like people who do chemotherapy, they're not allowed to be around people afterwards, or like any radiation, because like even sleeping in the same room, they get the same effects of being sick and stuff. Because I see that firsthand.
That makes sense. I haven't had enough radioactive materials. I've only had radioactive dyes put in me. And yeah, they let me go. I was told by another colleague that he came back into a lab with Geiger counters, and they detected him as he walked by after having a medical procedure that involved a radioactive dye. I didn't know that, Emily. That's actually interesting. So there are pros and cons to both. Also, we should point out that with burning like coal or gas, you are emitting some rather noxious gases into the atmosphere, including carbon dioxide. And so those are other concerns you would have with the traditional power plants. Yeah.
But aren't there also problems with the fact that we're cooling it all, and so we're making all this extra hot water in reserve, this extra heat, and we don't have a good spot to put all that extra heat?
Well, that brings up another interesting, I wasn't even going to talk about this, but the concept of heat death. Has anyone heard of heat death? Dimitri's on it. Here it has. Heat death comes from our understanding of heat engines. In life, everything really is fundamentally a heat engine. You think about it. We have our energy sources. Our energy on Earth is over 99% coming from the sun. And we have the sun causing all kinds of heat engines, if you will. Things like in Washington, when I was in graduate school, Washington Water Power was our electric company. And it's using hydroelectric power, good, clean hydroelectric power. And I'm a big fan of hydroelectric power. I've been watching too much Donald Trump, apparently. At least I'm not sounding like it. Hydroelectric power, though, is a heat engine if you think about it. Because what's happening? You have heat from the sun, warms up water. The warm water evaporates, goes up into the sky, cools, falls back down, higher elevation, and gives us the potential energy for using in the water power. So it relies on the heat cycle for it to work. If you didn't have differences in temperature, you wouldn't have the water evaporate and go up into the sky, and it would stop. Pretty much everything we have is a heat engine. So if, for a heat engine to work, you have to have a hot temperature and a cold temperature. What's the theoretical efficiency if the hot temperature equals the cold temperature? 0. And that's the concept of heat death. For every heat engine, because you're dumping heat at a lower temperature, what's happening is your difference between high temperature and low temperatures is getting smaller and smaller. And so eventually the universe could equal out so everything is one temperature. And if everything's one temperature, you no longer can have heat engines. And so that's the concept of heat death. You reach the point where you can't make a heat engine anymore. You can't have anything to convert energy. Okay, I spent a lot of time on that slide, more than I intended, as always. I've already said the Carnot engine doesn't exist. Real engines don't reach the Carnot efficiency for design reasons as well as very simple reasons like friction. It's impossible to build something without friction, so that's going to always divert some of your work energy back into heat. So that is in addition to the second law saying you can't make a perfectly efficient engine. You have the reality of friction that makes it so you're not even going to reach the ideal efficiency. Heat pumps. I mentioned heat pumps in class Monday. Heat pumps are heat engines in reverse. So in this picture, you see that is a Carnot cycle. Just like the Carnot engine, this is a Carnot heat pump. What's the difference? You put energy in. If you look at the direction of the cycle, for the Carnot engine, I better go back to the Carnot so you can recall. Not that one. Must be this one, yeah. For the Carnot, notice it's a clockwise cycle, which means that the expansion is at higher pressure, and thus you have a net work going out. For the heat pump, it's a counterclockwise cycle, which means you have a negative work. Work is coming into the system. And that work coming into the system is causing us to pump heat in the opposite direction that would naturally flow. Second law of thermodynamics, one of the statements, the Clausius statement, heat naturally flows from high temperature to low temperature. But the heat pump uses work to reverse the direction of the heat flow. So in this case, you're going to have, if you draw the stylized engine here, notice all of the arrows are reversed. For a heat engine, you had Q high is in, and then that split between Q high, Q hot, and work. We try to draw these accurately so the size of this plus the size of this equals this, because we have the relationship that says Q hot minus Q cold equals work. And so you should have the size of this is equal to the sum of the sizes of those two. So we try to draw pictures to illustrate that. Now, if we look at this heat pump, it's reversed. The Q cold is going in, the work is going in, and you see the width here is equal to the width here plus the width here. Because you still are going to have the change in internal energy for one cycle is 0. It's just you reverse the direction of everything. So in this case, all of the work you put in, remember efficiency was what you put or what you got out divided by what you put in. And so for a heat engine, what we got out was work and what we put in was Q hot. For the heat pump, what we put in is work and what we get out is Q hot. But the Q hot is not a conversion. We didn't convert the work into Q hot. We used the work to move heat. Because it's not a conversion, we can't use an efficiency. In fact, you're always going to have the Q hot bigger than the work you put in because the work you put in is being converted into heat at the Q hot. And so instead, we talk about a coefficient of performance. COP is coefficient of performance. And if you're using it for heating, what's the important thing you're getting out? What do you want to maximize? For heating, it's QH. If you want to heat your home, you want the Q at the high temperature to be maximized. So the coefficient of performance is that thing you want out, Q hot, divided by what you put in the work. Same heat pump. If you're using it for cooling, then the important thing is Q cold. So for cooling, I'm going to change color just to be maybe. For cooling, the important thing is Q cold. And so the coefficient of performance for cooling is Q cold over work. So we calculate two different coefficients of performance depending on what you're using it for. Notice, a heat pump can be used to either heat or cool because it's just moving heat. if it's hot outside, you want to cool your house, you set the heat pump up so it's going to draw heat from the house and exhaust it outside the house. It's going to be hot air coming outside the house, right? But it's going to cool the house inside. If it's cold outside, you want to heat the house, you just reverse it. So on your house, you can have a heat pump, and the heat pump can be set to either cooling or heating. And the heat pump will give you a coefficient of performance. Well, if it's a Carnot heat pump, then we can once again say the heats are proportional to the temperatures. So the Carnot coefficient of performance would be that, and you see the coefficient of performance, if temperature hot is equal to temperature cold, what's happening to my coefficient of performance? It's approaching infinity. Why? Well, it doesn't take much energy to move heat if they're the same temperature. And so if you have a small temperature difference, a heat pump will be very low energy required for doing heating and cooling. And of course, if I had done the coefficient of performance for cooling, you just would have had T cool on top instead of T hot. The coefficient of performance for heating is always going to be bigger than 1. And so these are very useful as long as that temperature difference is small. If the temperature difference is large, then the coefficient of performance is going to drop. So if it's, let's say, 45 degrees Celsius out, nice hot summer day, and you want it to be 20 degrees Celsius in your house, that temperature difference of 25 degrees Celsius is going to mean that your coefficient of performance drops considerably compared to what it would be if it was a lower temperature outside. And finally, entropy. Everybody has some idea of entropy. Everybody says entropy is the amount of disorder. That reminds me, Nathan showed me one of his problems that appeared to be incorrect on the reading quiz. We have a number of equations here on entropy. The one that the book was focusing on was if you have a constant temperature, the change in entropy is equal to heat over temperature. So if you add heat at a constant temperature, the entropy is going to go up. And for some reason, his problem said if you added heat, the entropy was going to go down. That would be wrong. So I'll have to go and check those over. But what is entropy really? Entropy, we call the amount of disorder. Go ahead.
I would say it's a probability that it's going to occur.
Okay, it really is. Did you get that from the tutoring, or because I told her that, or did you know that?
Oh, I read it.
Oh, you read it. Okay. So entropy is a measurement of the number of microstates in a macrostate. What's a macrostate? That's a state given by our state variables. Our state variables were pressure, volume, temperature, and the number of molecules. So we have one pressure, one volume, one temperature, and one number of molecules in this room. But we can have many different arrangements of the positions and speeds of the molecules to get that same state. And so the entropy is a constant, the Maxwell-Boltzmann constant, times the natural log of how many different ways we could arrange the molecules in this room to get the same temperature, pressure, volume, which is a large number. It's easier to understand as we talk about a two-die system. If I have two dice, my macro state will be the total roll. So macro state would be between 2 and 12. The micro state would be the number for each die. So for instance, if I roll a 2, there's only one way to get a 2. I have to have a 1 on the first die and a 1 on the second die. To get a 3, there's 2 ways to get 3. I can have a 1 on the first die and a 2 on the second die, or I can have a 2 on the first die and a 1 on the second die. So that has 2 microstates in its macro state. 4 has 3 ways you can get it: 1 and 3, 2 and 2, or 3 and 1. So there's 3 microstates, and you go on up to 7. 7 has 6 microstates: 1 and 6, 2 and 5, go on through. So when you go through that, the one with the most microstates is 7. And so if we calculate the entropy, we'd say this Maxwell-Boltzmann constant times the natural log of, that my actually takes 7 was 6. That's the entropy for my roll of 6. Or roll of 7, excuse me. Now, how is this useful? It's exactly what DJ said. The entropy is a measurement of how probable something is. Now, it's got a logarithm in there, so it's not just equal to the probability. But the higher the entropy, the more probable the system is. With the dice, if you were to plot the entropy as a function of roll, it's something that would just be like this. No big deal. But if you take the billions upon billions upon billions of molecules in this room, and you plot the entropy as a function of the temperature, pressure, volume, you come like this, and then all of a sudden it would spike up and look like it's just 0 everywhere, and then a spike of 1 and 0 everywhere. And so the highest entropy is going to be the one where you have virtually all of the possibilities. And so the second law says the most likely thing to occur is what's going to occur. That's another statement of the second law. Okay, I'm out of time. I'll see you again on Friday. No, I cannot. It would be tempting. I would love to drive away earlier. It's